Okay, let's start. My name is Tan Zhao. I'm a research scientist from NVIDIA. Today, I'm honored to host this talk from Andrew Sellergren. Andrew Sellergren has been at Google for 15 years, the last 6 of which he has spent developing models and the infrastructure for health AI. He has helped lead both training and externalization of medical foundation model efforts like CXR Foundation, Elixir, and MedGemini. He has co-authored numerous publications and patents in computer vision for medical imaging, as well as large language models and large multimodal models. He received his BA in chemistry from Harvard University. Welcome, Andrew.
Thank you, San, and thank you, Diana, also for the invite. It's great to be here. Can everyone hear me and see my screen okay? Yeah?
Yes.
Okay. Great. Well, my name is Andrew. I'm a software engineer on Health AI Google Research, and I'm going to be talking to you today about accelerating AI healthcare development with HiDef. HiDef stands for Health AI Developer Foundations. It's our new effort from Google. And I wanted to say that I don't use Zoom all that often, so I'm going to try and keep up if there's questions in the chat along the way. We should have plenty of time, but if I don't get to you, then we'll hopefully circle back at the end and have a great discussion. Great. First, giving a little bit of an outline, I'll talk about our mission as Health AI, and then I'll talk a little bit about what I see as the transition and the waves of AI that we've seen over the last 5-10 years, and before that, though I wasn't involved in that. And then we'll talk in depth about HiDef and how it can accelerate research and development, particularly a few different models. We'll have some demos and some deep dives into particular models, and then hopefully some time for questions as well. Our mission at Health AI is to catalyze the adoption of human-centered AI in healthcare and medicine. We call ourselves an impact-driven research team, which is, I think, very special and unique. I really appreciated it. What that means is that we're not driven by revenue, even though we sit within a large corporation, obviously, that is concerned with revenue. But we're really looking to broaden the adoption of AI and hopefully impact as many lives as we can. So we do that by partnering with other teams at Google, external companies, nonprofits, governments, anyone who is interested in assessing, developing, deploying some of these AI tools. And so far, we've authored over 150 peer-reviewed publications. We have a number of prospective trials, and then we also provide access to health-specific models, tools, frameworks, which obviously we'll talk a little bit more about today. Oh, slides are not changing. Oh, how about now?
Yes, it's now changing.
Okay, sorry about that. Thanks for calling that out. Okay, so talking a little bit about giving the lay of the land of AI and how it's changed over the last several decades. So obviously, I've only been involved in it for 5 or 6 years, but I would say that it's pretty clear we've had a paradigm shift in the last few years, but things have evolved quite a bit since the 80s when there was statistical pattern recognition, and then later in the 90s with handcrafted features, some shallow learning, some smaller networks. And then, of course, in the 2010s, there was the ImageNet moment, and I'm roughly going to call this AI Wave 2, or maybe refer to it as deep learning. Though obviously, deep learning hasn't stopped. These waves kind of overlap. They're mostly useful just to frame our discussion for today, and kind of talk about how things have changed and are continuing to change. So don't take these as hard and fast. in AI Wave 2, we were fairly focused on becoming superhuman at various narrow tasks and less on the generalizability that we're focused on now. And of course, with Gen AI in the last few years, there's been a big focus on being multimodal, having very rich expressive inputs and outputs. So it's not a simple model that's giving out a classification necessarily. It's obviously giving out text or images or audio and taking in all of those as well. So let's talk a little bit about what Google Health AI did in particular during AI Wave 2. Here we had focused AI applications across a number of modalities, including ophthalmology, radiology, pathology, dermatology. And even as a team, we were a little bit split among these. We worked all together and we shared knowledge, but there was still very much focused on domain-specific applications. We'll deep dive for a moment into CT. So even as I was joining the Health AI team back in 2019, this was still in the works. I was not directly involved in this. Oh, I should also say, I'm representing the work of a lot of different people here. So they're great people at Google and outside of Google as well. So I just wanted to be clear about that. So let's talk about the problem and kind of just give a lay of the land there. You can see here with this is a 57-year-old patient with no history of cancer. On the initial scan on the far left, I mean, even as a radiologist, it would be hard to see some of these findings. But this case was called normal, and maybe it's a hard case, but obviously, if we could call that before a year later, it turns into late-stage cancer that is much harder to treat. That's kind of the goal here. And if we can be as good as radiologists or better, then maybe we catch cancer sooner, have better outcomes, obviously, hopefully. But you can see it's a 3D image. It's quite a difficult task for human or for machine. So research and development in lung cancer detection and diagnosis was, screening and diagnosis was mostly focused on collecting and curating high quality data. There's a lot of ground truthing and figuring out the labels. How do you call cancer after 1 year, 2 years, 3 years, that kind of thing. There was a lot of heavy customization of the model architecture and the design. And then, of course, figuring out the best ways to set up the user interface for radiologists. So this is where most of our work centered. And you'll see that this is in contrast to how we approach things today. One of our focused AI applications was kind of, it was focused on ophthalmology, but it's unique in that it represented detecting hidden signals, coming up with new science and not just standard diagnosis. In 2018, our teams were able to show that you can reasonably well predict 5-year MACE events, the risk of heart attack, essentially, or adverse cardiac events within 5 years, just from the retinal fundus photos. So that's a pretty cool finding as well. So deep learning is not exclusively about diagnosis. It can also be about new discovery as well. But let's move on now to talking about AI Wave 3 and what we've been up to the last few years, how this has impacted the industry as well as our team. So again, the transition is not an immediate cutoff, but we've moved from task-specific models to more foundation models and multimodal models. So whereas the task-specific models, there was a lot of flexibility in the model design, again, with the architecture or with pre-processing and so on, we were aiming to get superhuman performance in very specific tasks. It did require a lot of heavy labeling and compute, and of course, it doesn't generalize well. Our lung CT model isn't useful for diabetic retinopathy or dermatology, but that can be okay as well, obviously. With foundation models, we still have that same constraint. They obviously don't necessarily generalize well across modalities. Of course, you could have a foundation model that takes in multiple modalities, but often we still have these domain-specific models, sometimes modality-specific models. One change, though, is that they're trained in a much more general manner. They have a much more general objective, which allows them to then be adapted further downstream. And this is a nice innovation because it means that the practitioners who are doing the adaptation downstream might need a lot less data, a lot less compute, and they might even be able to extend it to multimodal inputs and outputs. But again, it still requires pretty intense labeling, some supervision. So you need experts to identify which images are of a certain class or have reports and so on. On the right, we have these multimodal models, which I think represent an even bigger paradigm shift. They have a much more intuitive human AI interface. They're taking in all kinds of different information from the users. But in this case, then you could maybe combine the information you get from patient records, images, genomics, and the model might not care as much about what the format of any particular piece of information is. So starting off with talking about our efforts in just multimodal models and kind of figuring out what we can do with this new framework. We forayed into this with MedGemini a few years ago. This was a large multimodal model that we used to explore the possibilities in medicine and therapeutics. And at a very high level, what we did was to take our domain-specific image encoders and adapt them for Gemini so that they would have multimodal capabilities. There's somewhat confusingly two MedGemini papers, but they represent kind of different sides of the same coin. They're both adaptations of Gemini that are working with multimodals, some with a little heavier focus on text, some with focus on radiology, dermatology, pathology, genomics. Let me see. Oh, okay, that's going to show up. Those of you who came for hopefully some of the technical, the little bits that will be the most interesting to you will hopefully get that from this and beyond. So the innovation here that I think even for me at the time was quite astounding was that tokens are tokens to some extent. The model doesn't necessarily care how you encode the information that's being put into it, as long as you give it enough examples and give it some ability to adapt to that. In the case of Gemini and MedGemini, what we have is a series of image encoders for the 2D medical images, and those were actually trained separately and then frozen, and the images that get input to them are turned into tokens that then just get injected into Gemini as you would any other piece of information, as you would with any other text. So the cool thing there about this is that you can have a whole lot of training that goes in before you even touch Gemini. And we had plenty of custom 2D encoders that worked for chest X-ray, mammography, dermatology, pathology, And we were able to then train a little bit longer, combine those encoders into one MedGemini 2D that takes in image inputs as well as the original Gemini pre-training text, medical text. And these models obviously have a lot of capacity. I think they're kind of over parameterized for these purposes. So we got pretty amazing results with that. On top of that, we found that we could train a separate 3D encoder. So our first attempt at this was limited to CT, but it was mostly meant to be a proof of concept that you could do the same with MRI or an ultrasound video, for example. And again, it's all just tokens. So not only did we find that, okay, you can feed in a single image as 256 tokens or something like that. You can send in multiple images. So the model doesn't necessarily care that this is a video or a 3D image or a 2D image, as long as you give it something to latch onto with that. There's obviously a lot more interesting ways to do that, but I found it pretty amazing that it worked at all. And in some cases, the embedding spaces for these models, the image models, the video models, the text are not that far away from each other. They're potentially bridgeable just with a linear transformation, or a few layers that would adapt between the two. And that's pretty amazing. That's not necessarily something that is a given. So just a quick overview of kind of the image interpretation tasks that we investigated with Gemini. Our main task, I would say, was chest X-ray, and we investigated just for interpretation purposes a normal versus an abnormal task. We also did radiology, visual question answering, diabetic retinopathy, lesion detection, and dermatology classification. And we found with our custom image encoders, as well as additional data, that we could outperform Gemini Ultra at the time, and also the states of the art on most of these tasks, or at least approach them. That was the other thing. It was kind of, we weren't doing any much worse, if at all, than some of the best techniques out there. So that was definitely exciting. We also investigated AI-generated radiology reports for chest X-ray. So of course, this is kind of the holy grail, I guess, of radiology, is to be able to write automated reports. We wanted to not just measure the concordance with the original reports, but also to have radiologists judge whether these were clinically viable or not. And we found 72% of them were. So we further split this down into the normal ones, which are fairly easy to call. And then obviously we did slightly worse on the abnormal ones. There's a lot more intricacy there. And this is definitely not ready for clinical use yet, but it's a promising step, I would say. And it kind of shows us where we can go. But even from where I'm standing, where we were a few years ago, this was kind of seemed out of the realm of possibility, but it seems closer than ever now. Likewise, again, as a proof of concept, we attempted to do the same thing with CT reports for head and neck. And again, just reading these reports was pretty amazing. Only 53% in this case were judged to have the correct clinical outcome. So obviously we have a lot more work to do here. But as a proof of concept, I think it was very promising. And there are potentially still other ways that this could be useful even as it currently stands. For genomic risk prediction, we had an interesting way of feeding this genomic information where the PRS scores were actually, or the task was set up such that it was actually fed an image of the genomics and then interpreted that way. So it was a bit of, again, kind of shoehorning things in a little bit, but the fact that it was able to reach state of the art on most of the tasks, 5 out of 6, was pretty amazing. So now I see some questions in the chat. Okay, 70%, 72% is good enough. Yeah, I wouldn't say it's good enough. No, I mean, maybe I have high standards, but it is a promising result, but it's certainly not good enough for clinical use yet. But it gives us a kind of idea of how much farther we have to go. And yes, this was that was manual evaluation by radiologists, so blinded to the source of the report, which ones they had mistakes in, and which ones didn't. And can you please share the experiences on the modeling to generate meaning embeddings from 3D volumes? Yes, I will actually talk about this a little bit later because we use some of the same techniques for CT Foundation, which has now been released. So maybe I'll hold that thought for now. Okay, so what I'm mostly here to talk about today is Health AI Developer Foundations. And there's been a really great movement in open models over the last few years, as well as Gen AI. So the release of Llama and the follow-ups to that, as well as obviously DeepSeek and Mistral and many others in the space, has been really exciting. And our effort, of course, is Gemma. So Gemma 3 was just recently released. And I am personally very invested and excited about this because I think that if your goal, as ours is to broaden the reach of your AI, then what better way to do that than by putting into the hands of developers? There's a lot of opportunity for them to build things that we don't have time to, we don't have data to, we don't have expertise to. And I think that that providing the tools, the framework, the models to jumpstart this is a really exciting venture. So our first efforts in this space are mostly focused over here on foundation models, which I'll talk about today. But we're hoping that we'll also be able to release lots of tools, frameworks, sample applications, things of that sort. But we also want to meet developers where they are on places like Huggingface, Vertex, anywhere that it's easiest to build AI these days. And yes, to answer the question, will the research community be able to build upon your models? Yes, most the models I'm talking about today are already released. They're open weights. There will be more to come as well. And we are hoping to get as permissive as a license as possible for them so that people are free to build whatever they see most useful for that. To answer the earlier question, can you evaluate automatically? Yes, we can. I guess somewhat ironically, it's not really a technical issue. I think it's more of a standards issue. I think that as you get into automatic evaluation, it's seen as a lot easier to kind of game the metrics. So having radiologists in the loop who are the final judges of things would be kind of our gold standards. Is your institution using the AI apps you mentioned? If so, what are the regulatory procedures needed to use AI apps? Yeah, there's a long list of things that need to happen for a model to be used for as a medical device. But there are also other creative ways of using models within institutions, for example. So healthcare providers can often use things as workflow improvement tools or in-house analysis that can still have a big impact, but does not fall under the purview of regulatory. So we're not trying to build the medical devices ourselves, and we want to empower others too. But that's where we are today. What kind of GPU resources will I need to try out these models? That's one of the great things is you won't. For some of the models, you won't even need a GPU. I'll show you how you can do that. And yes, it will be doable in Colab. And if you want to fine tune the whole model, you might need GPU resources. But for some of the particular ways that you can interface with these models, you won't need GPUs at all. Okay, so as it currently stands, Health AI Developer Foundation's HiDef already has a number of models here. Deep Variant is our genomics calling model that's been around a lot longer than HiDef, but we're folding it in here and hopefully adding some improvements to it and making it more accessible. Then there's a series of foundation models for pathology, chest X-ray, dermatology, CT, which was released end of last year. Here is our bioacoustics model. And then very, very recently was TxGemma for accelerating the development of therapeutics. So first I want to dive into CXR Foundation, which I had the most, well, one of the models that I had involvement in and was one of our earlier models as well. So our innovation here is that health-specific foundation models can lower the barrier for AI development. So if you imagine your neural network, your model, as a stack of layers and they build up a pyramid, your foundation model is actually the base of this pyramid. It's a stack of layers that the output of which will be this general set of features for your input. This set of features are your embeddings. So we'll talk about that in a little bit more briefly. To adapt a model to a new use case, you only really need to add a new top to the pyramid in this kind of analogy or metaphor. So on the left case here, you can see that the traditional way of transfer learning is to start from something like an ImageNet model, and you basically start all over every time you do a new modality or a new task. And this is prohibitive from a resource standpoint, from a data standpoint. On the right, with the foundation model for a given modality like chest X-ray or derm or path, you need a lot fewer layers, a lot less data in order to adapt to this new distribution. And of course, you also need a lot less compute. So if you can take the foundation model as being very good to begin with for extracting these general features of a model of an input, then you have a lot less distance to go toward your task. And you can do this within a browser, within Colab, that kind of thing. So again, to kind of visualize this a little bit more analogously, if you have your typical model, your neural network as the stack of layers, you might be used to the output being a prediction, something like whether there's airspace opacity, whether it's present or absent. If you can imagine, just instead of one final layer that gives you a soft max value or some probability or some score from 0 to 1, instead of getting that as the output, we're going to chop off those last few layers and we get a much longer array of floating point numbers. These are your embeddings. So it could be 1,300 or somewhere on the order of 1,000 or more. These numbers, although they're not really human interpretable, are your embeddings. They're your features for this model. So along the way toward interpreting this input chest X-ray, your model has extracted all these things about it. Maybe it's extracted that, the size of the lungs, the size of the heart. There might be very intricate details about fractures or masses or nodules that it's found. They're all tightly entangled with each other. So that's one of the challenges. It would be great if they were disentangled and we could then pull them apart and know which ones were which. But right now they're kind of all compressed into this one long vector, this one array of embeddings. And of course, this is significantly smaller. So if you imagine you're starting with an input chest X-ray, it might be 3,000 by 4,000 pixels. So you're looking at a couple million integer values. And now we end up with 1,000 floating point values. So there's some compression going on here. We think it's more information dense. It's more useful for the downstream tasks. So on the left, we visualize here how we develop this foundation model. We take some care in deciding what training objective we use to create such a foundation model, because we want it to be general for a lot of different use cases. That is to say, we're not going to necessarily train it on every classification task that there could be. We train it on something, a much more general objective, like abnormal versus normal. So it's keyed in on detecting abnormalities in chest X-rays. We also, as of late, have used the full reports, contrastive learning. I'll talk a little bit more about the techniques later. But this is where we can leverage our resources to help the broader community. Obviously, Google has quite a bit of compute. We have a lot of data. We have great expertise, and we can put all of that into building the best possible foundation model for these different modalities. And over on the right, we hope that developers can then kind of take the last mile. So there's a couple different ways to do this. Up at the top, the strategy 1 and strategy 2 are basically what I mentioned before, that you could do in a collab. So taking these embeddings that are the information-rich representation of your chest X-ray, you can train a few layers, maybe even one layer, to learn, which ones are airspace opacity, which ones have fracture, which ones have pneumothorax. Sometimes it helps to have a few different layers so that it's a non-linear model. Down at the bottom, there's of course the ability to fine-tune the full network. So we've also now been able to release the models to do that, but we know that this is prohibitive for a lot of people. It's a very big network. It might require a lot more data, but we want there to be that possibility as well. Fun demos. Are your tools requiring FDA approval for developing? No, I don't. We will put that onus on those developing the models, but the license does permit that. But it's not. You may develop on top of ours, but we won't be helping or assisting, I guess, with any kind of FDA approval. You mentioned that you're not satisfied with 53% AICT reports. What would be the potential directions to improve? I think the biggest thing is the quality of our data and the amount of data that we have. We still, in terms of orders of magnitude, if you consider that we will train ours on several 100,000 CTs, whereas some of these networks may require billions of images to really get a handle on it. And I think also more sophisticated techniques for self-supervised learnings. Is there a specific reason why there is no MRI foundation model so far? Not any specific reason other than we have some data for this, but we haven't had time. And it's also each of these forays requires us to dig in and really understand a modality. From my limited understanding, MRI is also a lot more complicated in terms of how you can pre-process window level the actual images. So still to be done, but There's also opportunity for others out there to develop that. Yes, the data that we're using for these foundation models is definitely de-identified. That's a good question. For these foundation models, do we need large data to train on a new modality that the model didn't see before? Probably. I mean, I would say it depends on how big the distribution shift is. So with if you were going from, say, chest X-ray to abdominal X-ray, maybe not as much data, but going from MRI or CT to MRI would be a much bigger distribution shift, or going from any 3D spatial model to, say, video. Is CT Foundation model available worldwide? Yes, it should be. There's a link at the end. Let's see if, whoops, that didn't work. I will probably have to provide that afterward. I'm not sure why it's not showing up. Yes, we do have plans to make CT Foundation open weights. It's in the works, but and what about a decoder part for synthetic? I'm not sure about that. That's something maybe we could consider. Rough estimate, I would say order of months, I would hope. So step one for the non-medical pre-training, that's mostly, we're taking that kind of as a given. So the models that began as natural image models, obviously there's already a lot of work going on in training on JFT 300 or JFT 3B ImageNet. So we start from that. I don't actually think it helps all that much with medical images, but that is something that we start with. Yes, we do have model cards for the foundation models. How are the data sets and labels collected? We do often partner with institutions to leverage their already de-identified collected data. And we also have on-staff experts who will, radiologists, dermatologists, pathologists, who will help us with further labeling. Let's see, I think I have quite a few more. I'm going to keep going for now so that we can hit everything, but these are great questions. Okay, so let's do a demo real quick because those are the most fun anyway. So these are Huggingface spaces made by another great engineer on our team. And so you can play around with them, but this gives you an idea of the power of a foundation model like CXR Foundation. So there's two possible tasks that you can do here. One is a data efficient classification and one is a zero shot classification. So data efficient just means that you only need to train a new model on, say, sometimes on the order of 10, 100 images for it to adapt to a new distribution. Zero shot means that you can formulate your classification without any new training. So we're going to look at the zero shot case. So these images are, oh, I see. I haven't chosen. Okay. So these images come from the NIH chest X-ray 14 data set. So there's 100,000 of them, but this will just pick a selection of them. So once you pick a particular condition, it's going to load up, say, 40 images, and it's going to roughly pick 20 that have an airspace opacity and 20 that do not. This upper left is going to be your label for this. Now I'm going to compute the embeddings in the background. So it's going to send the images and return with that layer of floating point values that represents information rich about this. And then I need to just formulate two different prompts. One is going to represent the positive case and one is going to represent the negative case. So this corresponds to roughly to language that you would see in a radiology report. So some mention of the words aerospace opacity is going to correlate with positive, and then something like no evidence or normal is going to correlate with a negative. So you can see with these two different prompts, you get an AUC. It's highly predictive. Of course, airspace opacity is quite an easy case, so we can do a different one, which is fracture here. Fracture and pneumothorax are a much more difficult. Fractures might be acute or old or very, very hard to see. Pneumothorax is kind of confounded by the presence of lines and tubes, and it can also be quite subtle. So with fracture, you can see if I use these two prompts, one is just fracture, one is no fracture, we get not a great AUC of 0.61. It's not super predictive. But if we change this to something like rib fractures and then filter this down to be no evidence of fracture, we can start playing with it and getting higher AUC values. So kind of fun. Path Foundation is a tool for histopathology images. So these are obviously massive gigapixel size images, and somewhat prohibitive to be training on. But again, by computing embeddings for some of these images and patches, we can do this within a browser and much more tractably. So what we're going to do here is draw a section of tissue that we want to find something similar for. So here is, this is an example of malignancy within this. And we're using, TensorFlow.js to train a model within to find similar tissue. And now we asked it to find very similar. And let's do this again with a slightly higher viewport. So now it's looking at all these different patches. That didn't work as well as I would have hoped. I think it froze. I gave it too much. So it has found some within this area, which is another area of malignancy, but definitely fun for you all to play with. Yeah, okay, so we will get to TxGemma shortly. I'll go a little faster through some of these. So zooming into CT Foundation, which was released recently, again, for some of the technical tidbits that people might be here for. Our imaging coders, the objectives that we use to train the very general case, the general objective, we had a lot of success with the COCA models. They have two objectives: contrastive learning and captioning. So we provide them with an image text pair, starting with 2D images, 2D medical images. So this might be a report or a label, and there's a image tower, a text tower. There's both a text encoder and a text decoder, and the model is trained to generate a caption from the image. It's also contrasted between the text and the image. And then on top of that, we've added even more self-supervised objectives like mask auto-encoding. It kind of all works together. From there, we go to 3D. We pass everything in as tens of thousands of patches from the original CTs. And then there is some attention pooling that happens to reduce that down to a tractable a number of embeddings. And these were what were actually fed into Gemini in the efforts I mentioned earlier. But now we're encapsulating them just as a standalone video COCO model, and there's a hosted API for this. This obviously represents very extensive information compression, which is part of what we can leverage to be able to train something in a browser or to do similarity search or those kinds of things. So you could take a CT volume, which starts as 300 megabytes, maybe even more, and what you're left with is only a few kilobytes. So we're talking about, tens of thousands compression. You might have a database that's 20 terabytes, and you could reduce it down to under half of a gigabyte. Where we found this to be super useful is with improving times for rapid testing, prototyping, figuring out where there's signal and where there's not. And you can see that even training small nonlinear models on top of these embeddings, we can approach decent performance on a number of different difficult tasks. And that's across body parts from head, chest, abdomen. Lung cancer, as we mentioned earlier, is a very difficult task, and we're still doing fairly decently with it as you get into the tens of thousands of images. I'm going to skip over talking a little bit about here, but it is our AI tool for bioacoustics, also available. With it, we were able to detect tuberculosis from coughs with pretty good signal. For reference, our CXR model gets about 0.84 AUC on the same data set. So it's pretty exciting. Much more recently, our first, I guess I would say, multimodal model release and our first generative model release was TxGemma. So this is a model for therapeutic predictions from drug information. I probably don't have to tell most people here, but drug development is very, very hard. It's very expensive. Most drugs fail in this development process. And so anything we can do to speed this up, make it lower cost, make it more efficient would be welcome. TxGemma is specifically trained to understand and predict therapeutic entities through the whole discovery process. So it can help discover promising targets, even predict clinical trial outcomes. And it's state of the art on very reasoning intensive chemistry and biology tasks like humanities last exam. So the innovation here is, again, just that drugs can be represented in text format. You can encode them as this small molecule or this protein, a sequence of amino acids, the nucleic acid as a sequence of nucleotides, and feed them into the model. From there, again, the model can kind of latch onto the massive amount of data and figure out the right associations and causations. So TxGemma's tasks encompass classification. So an example would be, will this molecule be able to cross the blood-brain barrier? Regression, the ability to predict drugs' binding affinity. And generation, can you predict the reactants from a given product? So we see it as a very useful tool, and that's how, for example, it's been hooked up as an agent into Gemini as well. I have a short little sort of vignette that kind of demonstrates the capabilities here. So here we're narrowing down on the list of promising drugs. Would this drug be mutagenic? What are the toxicities of a particular drug? Can we predict whether it will pass clinical trials? and which one is better suited for further development. So there's 3 different sizes, again, optimized for different purposes and potentially useful in different contexts, and all available on the link that I'll share at the end. So just to recap before we dive into more questions, I talked about our mission and the transition from deep learning to Gen AI, a lot of our recent developments there, and then I hopefully gave you a pretty good overview of high def and how you can use it to accelerate your own research and development. I'll leave this link up here with a QR code. Okay, I think I have quite a few questions to answer here. Okay. Has there been cases where a model was able to detect something a radiologist missed? Yes. Obviously none of these are being used clinically, but we have seen cases, both sides of it. So cases where, particularly with the CT model, where a very subtle finding was found by the model that was not. Sometimes it's just a matter of what could actually just be commonly excluded from reports, but the model might be more verbose about something, so that's fine. We just spoke to the TxGemma model, so hopefully that's good. Are the data used to train these foundation models available for public use? Some of it is, some of it is not. We do our best to give access to as much data as we can. For chest X-ray, for example, MIMIC is are great partners of ours, and there's a massive data set there. Chexpert, chest X-ray 14. So there are a lot of, and then on the flip side, there's actually data sets that we do not have access to because they're non-commercial use. So if you're interested in using those, you can. How do you prevent effects like catastrophic forgetting? I think that's definitely our biggest challenge. When we train models like MedGemini with new information, we often have to feed in the old training data as well. So some of the natural images, some of the natural text, non-medical, because we want the model to retain its original capabilities. But there are newer techniques that we're finding that are really useful toward that end, like distillation. That's how Gemma 3 was mostly trained. Reinforcement learning is a new one we're foraying into. Yeah. Would you expect the CXR Foundation model to be usable for X-rays of the spine? I think so, yeah. Especially if you're talking about additional training. Again, it's always going to depend on how much data, how much the distribution shifts. But that's the nice thing about the embeddings models, is even if they are not useful enough for your final task, they can give you a sense of how hard the task will be. So if you trained an embeddings model with CXR Foundation for spine X-rays, you could find out how much signal is there. And that might give you, or you could, plot the scaling law and figure out how much more data you might actually need. And it's certainly a lot easier to do that than to train your own model from scratch without knowing how performative or performant it would be. Sorry. Is there any reason why Google Health did not target foundation model for MRI? Yeah, I mean, I can definitely say it because it's hard, and we're gonna, we wanted to. Any one that we dive into, we want to give our full attention. So I think we felt like CT would be more, given that X-rays was already in our wheelhouse to some extent, and CT is more or less a 3D X-ray, right? We had some sense that we would be able to do it and have the foreknowledge, but we obviously still have work to do there as well. So. For the non-medical pre-training, will it interfere with model performance? I don't think so. I think it should only help, really. It doesn't help as much as people might think, but it does help in the sense that non-medical pre-training, you will get things like, what is an edge, and what is the spatial awareness of an actual scene, that kind of things. Are there plans to incorporate electronic health records? Yes, we have some efforts into EHR, and I think over time, these are all converging to some extent. Again, they're kind of getting to be able to speak each other's languages. So EHR is definitely one that's top of mind. We have a whole open source effort in that space as well. So definitely an exciting time. Only normal versus abnormal. Yeah, interestingly, that was very effective as a general training objective, since that's essentially the task of a lot of chest X-ray radiology work, is to identify, is there a clinically significant abnormality? Do we need to follow up on something? And that's not always obvious. There may actually be abnormalities that are not clinically significant. So it's not as easy as it might sound. Does zero shot mean no training after pre-training? Yes, that's right. It's just fed two different text strings and the original image, and it figures out which one is closer to the image, whether it's a positive or a negative. So I wouldn't say it's necessarily useful for clinical purposes, but it's again, gives you an idea of signal or how you might tweak things for further. Mentioned that high def was first trained with natural image, then transfer learning to lung CT in medical imaging. Anatomical scale is very important. There are papers showing, did you consider spatial resolution as one of the input embeddings to adapt to different data? Yes, we do struggle with this a lot. We want, for our CT Foundation model, we attempt to take in the model at the original resolution, which is kind of crazy. Something like 512 by 512. That's another reason why we went for head as opposed to a different body part, because we could potentially fit the entire volume into memory. But I think that adding spatial resolution or different signals as another part of the input embeddings would be very promising. Oh yeah, for CT, did you use the entire volume? Yes, for the most part. There were some cases where if there's too many slices, we would have to pick and choose which we had to sample them. But that was one of the sort of crazy aspects of it, is that we wanted to just be able to take the entire volume and feed it in. So no downsizing of the resolution, or there is patching, but we try to retain all the original patches. How to visualize and interpret embeddings after the CT image compression. So there's a lot of great tools out there for visualizing embeddings. There's the traditional ones like PCA, Principal Component Analysis, or TSNE, or UMAP, are all great ways of visualizing the embeddings. And that's where you can find if certain clusters are, say, normal, or maybe different body parts are clustered in one area than another. AUC for TB is 0.739. Yes, that was from cough, detection from cough, whereas from chest X-ray it was 0.84. Yes, the model is definitely picking up sometimes things that the radiologist didn't. As I said, it's not anything that's like a novel signal necessarily, but it might be something that tends to be left out of reports, or it could be something that's very subtle. But I think that's also a good case for why you would want to collaborate between radiologists and AI, or experts in AI, is because they can complement each other. Okay. AUC of 0.74 useful clinically. I don't think so. It's probably, it would be dependent, of course, on choosing an operating point, and you could potentially scale it to be where you want it in terms of sensitivity and specificity. But you could use it for things like triage. And in the case of TB, you could use it for determining who you wanted to get a chest X-ray of, who you wanted to do sputum sampling of, which is much more expensive. So that's one of the ideas here as well, is that they're for a chest X-ray, if you wanted to do normal versus abnormal, for example, again, maybe you are saving a radiologist time and not having to have them read every single image, but only the ones that are known to be abnormal. Interesting. I don't know about VOCO, and yes, there's definitely a lot of really cool work out there in segmentation, which we haven't forayed into as much. To be honest, I mean, I think the nice thing about models being out there is that you can combine them all, right? You could take your CT Foundation embeddings and combine them with the embeddings from, or fuse them with a model like VOCO. And for any particular task, you would hopefully get better performance. I know we're over time, but I'm happy to stay for a few minutes to keep answering. NIH chest X-ray contains annotation errors. Yes, we've done a lot to relabel those actually and improve them with radiologists. And we have also tried it on MIMIC. And MIMIC was part of our pre-training. CheckSpert is not, it's non-commercial, but we've often evaluated on CheckSpert. So I think those are both very useful as data sets. Yes, for pathology, that was search and retrieval. Probably it is possible to do zero shot. Well, sorry, that's maybe not true yet. We have versions of Path Foundation that are text aligned that would allow you to do zero shot like that. I can't remember if the Path Foundation we released is a image only model, but it's certainly possible if you have a text aligned image model. Yes, the gigapixel image is divided into patches, and they're all, and we do also have efforts. There's our recent paper, Polypath, where we feed the whole slide in, just like we feed the whole CT volume in. So there's again, more exciting developments there. We had a team in London that was working on OCT, but I'm not sure about foundation models for that. I wouldn't rule it out. Again, AlphaFold, I think, could be complementary to TxGemma. I think it's a really exciting world in which we can imagine that a lot of these different things are tools, and maybe an LLM like Gemini is an orchestrator of those. So you could ask it to analyze something with AlphaFold, analyze something with TxGemma, and get the best of both worlds. I don't know if, I think you would be pushing the boundaries to have this foundation model run on device, but as we get more performant devices and also smaller foundation models, I think that becomes more viable. Yes, responsible AI is very important to us. We have whole teams working on it here, and we interface with them very closely every time we do a release, or even as we're training to try to get things right. So that's very important to us. Here, predicted TB with 0.72. I believe this was an in-house data set from one of our partners in Zambia, but we have a number of other data sets out there that are public. Of course, they won't have cough sounds along with them. That was part of why it's a little harder. But for chest X-ray, there are existing data sets out there like Montgomery from the NIH. Ultrasound foundation model is definitely on our radar as something we're potentially interested in. Where will the breakpoints that these models can be used in clinical trials? I don't think there's anything stopping it. It's just that we're not the ones that want to take it there. We had previous efforts like that, but we, for various reasons, decided that was not our best, the best use of our resources. So I don't think there's anything stopping other models being components of medical devices or clinical trials. Modality translation is an interesting one. I don't think we've ever really, in some sense, they are being all translated into text, but not explicitly, I guess. What is your definition of success? That's a really good question. We want uptake. I mean, we are very interested in, I think TxGemma has already been downloaded a few tens of thousands of times, but we don't want it to just be downloaded. We want it to be used. So we really want to see, that's why we're trying to hear from the community and know what it's being used for, how it can be improved, make sure that it's actually being adopted, and also try to partner very closely with others to know that they're taking it the last mile. What are their barriers to taking it the last mile, and how do we? So, our definition of success, my definition of success, is true impact on patient lives, and it could take years for that to be realized, but that's okay. We want to just provide the tools now. I don't think that the CT image, they are, I guess, interpretable in the sense that you could assign signals to certain, again, with the advent of tools like TSNE or UMAP or PCA, but they're not human interpretable. That is another kind of holy grail, would be disentangling those embeddings so that they were human understandable. For if no additional training, how could you know an image has a specific disease name? Yeah, so you're kind of guessing a little bit. I think this is where having we talk a lot with radiologists. I think there's ways we can improve that in the future so that it doesn't have to be as specific. But for now, you could simply look around and figure out what is the language that's used to diagnose something like this, or to call out this finding. The connection between TxGemma and Deep Variant, mostly by our team so far. There's a lot of people working on both. And which tools does it build on? So I think mostly it builds on Gemma, which is the newest open source, and then the data that we have in-house for that. How can I start playing with TxGemma for pharma? No background in pharma. That's a good question. I guess I would just start by chatting with it, and maybe also chatting with something like Gemini and seeing, you can even kind of play them along with each other, ask for what would be useful to ask a model about a drug target, or tell me more about this drug or something like that, and then plug it into TxGemma. Synthetic data and medical AI, yeah, we're already using some, not extensively. I don't think it's a free win, but it has a role certainly for things like privacy preservation, augmentation, things like that. So even if our model itself is not, it is cleared for the use in these. So there are plenty of other ways for foundation models to be used in clinical use. They can be SOUP, for example, software of unknown provenance, and they can be treated as such for submitting for regulatory purposes. So there are ways that it can still be used for medical purposes, even if this model itself is not a medical device. Yes, there's definitely hallucination possibilities. We're working hard on how to prevent them, but I think the best advice is to figure out other guardrails that help filter them out or control them, so that you can be sure you're getting high quality outputs. I wouldn't think that CT Foundation would be super useful for MRI, but I could be wrong. Maybe it's a good starting point. Pre-processing CXRs, you shouldn't have to worry about that for CXR Foundation. We do our own custom. In fact, you can send in the whole DICOM, I believe, and we will handle it that way. But there's a lot of great papers on the pre-processing of chest X-rays. I don't know of any surgical image foundation model. MedGemini took in some surgical videos, but that doesn't mean there isn't one. I just don't know of any. Oh, great. I didn't even know that Persistent is using, oh, thanks, Claudio, using AlphaFold 2 and TxGemma as complementary tools. Okay, hopefully I can get these last few. Is there a plan for, we have not delved into federated learning, but that doesn't mean it's not possible. I think it's very difficult to coordinate, but that doesn't mean it shouldn't be done. And we are integrating text reports. That's part of the training for our foundation models. So the contrastive and captioning. What's the best way to join your team? So we have a lot of postings on careers.google.com. We also hire interns, student researchers for those of you in PhD or master's or undergrad programs. Is scanner heterogeneity handled? Yes, in the sense that we take in images from lots of different scanners, and I think the models are pretty robust against that. It's not perfect, but it is one more thing that the model considers. Okay, that was a lot, but hopefully I got to everyone's questions. I really appreciate everyone joining. It was a real honor to be here.
Thank you, Andrew, for the wonderful talk. So if anyone has a question, you can still welcome to email Andrew or this email on the screen and the QR code. For the recorded video, if we got the permission, we will upload the video to our YouTube channel. Thank you all for joining this talk. Have a nice day.
Thank you all.